So here we have the diagram from the problem previously described, and just to run through what the problem's asking for again, the question is a 12-volt car battery is connected to a motor with a pair of 6-meter long AWG10 copper wires. What fraction of the power supplied by the battery is dissipated in the motor? And so for the first part of this one, we have to collect the relevant equations that we need. So the first bit we have here, we drew out the circuit diagram, which is self-explanatory, 12-volt power supply, 2 6-meter long wires, so that's a total of 12 meters total of this wire. And then we have Rm equals 2 ohms, which is the resistance of the motor, 2 ohms. So what we're finding is RC, or R of the cables, or R of these wires, whatever you want to call them. I just called it RC, the book called it RC, so we're going to go with that. So for RC, what we've got now is the resistance of the wires equals what? And we have to look up what equations we have that might be useful for this. So the first equation we have that we've looked at just previous to this is there L over A, just resistivity times length over area. And so this is our first set. So we should be able to first start by plugging in different values that we have from this. So what is the resistivity first off? That's something that wasn't given in the problem. It didn't say with the resistivity of blank. It just said we're using copper wires. And as we learned, each material has its own set of resistivity values. So what we need to do for this is to look up some resistivity table. So I've taken one here right on my iPad. Let's zoom in on copper. Copper, we have 1.72 times 10 to the minus 8th ohm meters. So that's our first bit of data that we need, so we're going to write that one down. I'll pull it over here for now. So we're going to do equals 1.72 times 10 to the minus 8th ohms per meter. Because remember, it's a length, it's how much resistance per 1 meter of things. Sometimes it's in feet too, but meters is more standard. So we have this, that's our first bit, that's our row. I'm just going to put a big parentheses around that to keep it nice and clear. And now we have our length, which is our next one. Our length is easy, it's 6 plus 6, so that's going to be 12 meters. Okay? And then we have our last bit, which is our area. So again, it didn't tell us what area we had of the wire, but it did tell us that we were using AWG10 copper wires. And AWG is a wire standardization size. So for that, we can go to find out exactly what the diameter of the wire is. So if we go here to another site, and again, you can use these sites or anyone that has some data, your book has it too. And we zoom in on, there it is, AWG10, and we go across. For conduction diameter in millimeters, we have 2.588. So we're going to write this down, and that is diameters in millimeters again. So we're going to have to change that a little bit. We're going to do 2.588, and remember we have to move our decimal place over. So this is going to become what? Times 10 to the minus, centimeter is 2, so this is 3. And then we're going to do that. Remember, so this is a diameter here, and for this we need the area. So what is area of a circle? Just so we have this again, the really quick equation, area equals pi r squared. So this is a diameter, so we have to divide it by 2. And then we also have to multiply it by pi. And this is an r, so once we've already done this, I'm going to put kind of a bracket around it. We're going to square it too. And that's going to give us our area of this piece. So this came from a table. This is the unit change because we're going from millimeters to meters. This is divided by 2 because you want the radius, r, pi r squared. So we have the diameter here, we have to bring it to the radius. This is the r squared value, and this is the pi on the outside. So again, the resistivity value we needed a table for. The diameter of the AWG10 we also needed a table for. Oops, sorry, got a little off there. So what we're going to do now is we're going to solve this out. RC equals, I'm going to plug this right into the calculator so we get a nice clean answer. So it looks like we are going to get 0.041, so we're just going to say 4 ohms. So that's saying that the resistance of the cables, which are these two individual cables, is 0.4 ohms when the resistance of the motor is 2 ohms. So right off from looking at this is significantly bigger than 0.4, where this is much more resistance than these wires. So what we can tell from that, without even doing any more, is that the majority of the resistance is from the motor and not from the cabling. So what we're going to be able to do now, though, is the question asks what fraction of power is being supplied by the battery is dissipated in the motor. So we have to find the total power too. So in order to find total power, we need to find total resistance, because remember, I total equals V total over R total. And that's for the entire circuit, because we're trying to find the total power. And remember, what is total power? Power total equals current total times voltage total. I wrote it wrong. Oh well, you know what I'm talking about. So I total equals V total over R total. So what is our total V? Our total V is, well, just 12 volts like we had up there. So that's an easy one, 12 volts. And then our R total is going to be what? Well, we have our R motor and we also have our total RC. So that's going to be 2 ohms plus 0.04 ohms. And that's going to be in parentheses because that's a single thing. Okay? So when we solve this out, our I total is going to equal what? Our I total is going to equal 5.88 amp, right? 88 amps. And just for curiosity's sake, I'm going to write down here our R total equals 2 ohms plus 0.04 ohms. And again, we just did this in the step. I'm just trying to keep it nice and clean. So our R total is going to equal 2.04 ohms. Okay? And so now we're going to look at power. So the power total is going to equal the current total times the voltage total. So we have our current total, which is up here, 5.88, and we have our voltage total, which comes from here. So power total equals 5.88 amps times, what did I say, 12 volts, right? 12 volts. And so the power total is going to be 70.57. And what's the unit for power? It is watts. Cool. So 70.56 watts is the total power in this entire system here. So now the last piece of it is it's saying what fraction of power supplied by the battery is dissipated in the motor. We're going to get power of the motor equals, remember we can do P equals VI, but we can also substitute IR in there. Let's just do that real fast. So we got power equals IV, and remember we can have V equals IR, so we can also have power equals I squared R, because remember we just plugged V equals IR into this part, so we get two I's and then the R. And this is going to be of the motor. And so that's going to be 5.88 squared, because look, that's the current total, so we have the current total, and we're also going to have the R of the motor. The R of the motor comes from up here. We have essentially, here we go, 2 ohms. So we have equal times, excuse me guys, 2 ohms. And that's going to equal 69.15 watts. And so what is this percentage of this? If you do 69.15 over 70.56, and that's in watts, equals what? It should be 0.98. Move 2, so that's the percent, equals 98%. So essentially 98% of the power, 98% of the total power is being supplied by the battery and dissipated in the motor. And that's because this resistance is so much greater than this. There's so much more heat loss than over here. And that makes a lot of theoretical sense. So I'm going to post a book solution up on this one. I just wanted to talk you through it once in case that would help at all as well.